Okay, guys, here's part two of force and motion. Let's go ahead and start off with, we talked about inertia a little bit. Let's look at mass right now. We'll start with mass. Okay, the amount of matter in an object. Okay, so that's going to lead us to a really interesting thing now because we have the equation in Newton's second law. Acceleration is the result of a force opposed by a mass. Okay, so look what happens here. If I have more mass for a given force, my acceleration is going to be lower, right? This is an inverse relationship. Just think about it like this. You go to kick a box, and it's a really light box, so it has a small mass. You kick it with a certain amount of force, it's going to accelerate really quickly. But now if I have a heavier box, it is going to take a lot more force to get it up to that speed. So let's take a look at this picture here, right? So I'm throwing the baseball with 34 newtons. I'm throwing a softball with 34 newtons. There's a little bit more mass to the softball, 0.2 kilograms versus the baseball, 0.14 kilograms. Look what ends up happening to the acceleration. Because the mass was higher, look what happens to the acceleration. Only 170 meters per second squared versus the baseball, 240 meters per second squared. So that kind of tells you a little bit about why the baseball pitcher needs to be maybe a little bit further away, right? But if you actually go into the physics and reaction time, the softball players got it a lot harder. So interesting, right? Okay. Now that we've looked at mass, let's go back and take a look at acceleration, right? Let's take a look at acceleration. Okay, acceleration, we know this from before. Acceleration is meters per second squared. That's the unit for it. Usually, Newton's second law in a lot of books is incorrectly written as F equals ma. This is algebraically true, but it's not the natural law. Okay, the natural law actually says that acceleration is a result of a force being opposed by a mass, so overcoming some sort of inertia from a mass, right? Remember that inertia and mass mean almost the same thing. Okay, but it's a change in v, and it's always caused by forces, okay? And here's an example here. Let's take a look at get this guy out of the way, something like that. Let's blow this up, so take a look at it. Okay, so in this case, we have same baseball, right? So it's going to be 0.4 kilograms. But look at the difference now. Big Major League Baseball player throwing it at 50 newtons versus the school child throwing it at 17 newtons, right? Not as serious here. It doesn't look like she's going to, fart or something like this guy is. And look what ends up happening here. The acceleration that the man's able to generate for more force is much higher, right? So the more force you apply for a given mass, the higher the acceleration. You're overcoming that mass with a lot more force. Okay, cool. Let's put this over here. Okay, let's go now to net force. We're going to look at net force. Okay, so that should be on your second page. Okay, net force means the sum of all forces acting in all directions on an object. Okay, objects that experience balanced forces, that means it comes out to 0 newtons. They're at constant motion or not accelerating. Let's look at an example of that here. Okay, so if I have two people pushing a box in the same direction, so let's look here, that means his vector and her vector would add up together, and look what ends up happening. You end up adding these head to tail, and look, bam, they get more force. The net force would be in the positive direction here. Now, if they're pushing against each other, right, they're pushing against each other, her force would be going this way. This force might be going this way. You would have to, since they're going opposites, you end up having to subtract, right? So you end up with a net force of some value going this way, right? This would be small arrow would be the net force, right? This would be the overall net force. So you get rid of these, right? Okay, so that's how net force works. Of course, you can do this in the up and down direction as well. So don't think we're just going to do these in one plane, right? This is going to happen in 4 different directions, and we're going to have to use the Pythagorean theorem. Okay, this brings us to a really interesting term, terminal velocity. Okay, terminal velocity is meters per second. It means it's not how fast, it's not the max speed you'll go when you die. It's not that. The max velocity possible in the presence of atmosphere while falling. Okay, and this is important. Okay, so the net force at terminal velocity is 0 newtons, which means there's no acceleration. So look at this. That means if I'm a parachuter and I'm falling down, if I'm at terminal velocity, that means the pull of force gravitational is equal to the force of drag or air resistance going up. Okay, and that means my velocity would be constant. Okay? It doesn't mean I'm not moving, it just means I'm not accelerating anymore. Okay? All right, so let's look at what is free fall then. Go back to free fall. Okay? Objects only experiencing the force of gravity, or force gravitational, that is called free fall, right? So a feather falling down, drifting back and forth like this would not be free fall because there is force drag acting upward on it, right? But I have a video that I can show you that shows if you were to pump all the air out of a tube, like on the moon or something, a bowling ball and a feather would drop at the exact same rate, right? There would be no air resistance. Let me see if I can just show you a little clip of that real quickly. That's not it, it's a lawnmower. See that? Even though that's a feather, look, they're dropping at the same rate. Cool, right? Okay. All right, what else we got? Inertia, gravity, free fall. What else we do with those? Conservation, momentum. Okay, let's do weight real quick. Okay, weight, this is important. Weight, the other word for weight is force gravitational, FG. These mean the same thing. Do not ever forget that. And since it is a force, it is also measured in newtons. Anytime you see the word force, the SI unit, the System International unit for it is the newton. It is the force exerted on an object's mass by the gravitational field. Okay? It's also measured in newtons. Different force gravitational happen on different planets. So you'll weigh differently on the moon. I think I want to say it's like a sixth, weigh a sixth or a 12th of what you would on Earth, but your mass is always the same. Okay, so that's very important. That means you could leap at higher speeds easily on the moon because you have less force pulling you down. But you have to be careful because your mass is still there, and if you don't land correctly, you can still crack your ankle, snap your toes, and stuff like that. So you can still get crushed by a spaceship in space, even though you could lift it very easily. Okay, so just be careful. Okay. Now, what tells you your force gravitational on Earth is a scale, but I want you to be very careful with that. The scale is not actually measuring your weight, and the reason I can tell you that is because if this elevator were to go up and down, you feel heavier or lighter depending on the direction you're going, right? That's because this is opposing force gravitational. So we'll touch on this a little bit later, what a scale is actually measuring, but it's actually not force gravitational. All right, so just be very careful with that. All right, let's see. Have we gone over everything? We got conservation momentum. This just means an equation m times v is equal to momentum. P is momentum. It's a Greek for protestai, which means to fly or leap. And m is mass, measured in kilograms. V is velocity, measured in meters per second. And conservation of momentum is really, really cool. It's an extension of equal and opposite forces in Newton's third law. And what it ends up saying is that for a given system, if you have no external forces acting on the system, and it's all just maintained within these two girls here, what you'll end up having is an exchange of momentum that I have a video of this we'll show in class. You'll have an exchange of momentums that are consistent with what you started out with. You're going to have the same m times v going in as you have the same m times v going out. And you might have seen a Newton's cradle with those little metallic orbs that go that click back and forth. Okay. All right. So that takes us through pretty much all of our vocabulary. Again, pause and study this as much as you need to. If you have any questions about any things, please ask me. Good job.